So I think what I want to do certainly today. So Wednesday, I'm actually going to be attending a virtual conference. So we will not have class. I think in this time zone, the conference is like from 6 a.m. to 11 a.m. or something. So what I'd like to do, at least for today, is I think there's enough things where things in the homework that people are struggling with that I think, partly maybe I just didn't do a very good job of explaining them or doing enough examples or whatever. So I'm pretty open. I don't have like a lot of stuff planned, but I'm just, I would love to go through some things on some of the homeworks that people are still working on, maybe do some examples, answer some questions. So I can come up with some things to do. Also, if you're like, I'm really struggling with thing X, and if you could do an example of that, that'd be great. I'm open to those kinds of suggestions as well. So, so just as a reminder what we have so far, and very soon, so probably later this afternoon, I'm going to publish Module 6, which will be doing AGDA stuff. You can do it on the AGDA Pad website, and that'll be due, officially due like the Wednesday after spring break. So you can work on it over spring break or not as you wish, or you can start it now and then forget about it over spring break, or you can start it right after spring break if you whatever. So got so like some Haskell stuff, and like the ones about this one is about like folds and fold rows trees and all that kind of stuff. Lambda calculus, and then this one is about simple type lambda calculus types. Very hard. So any particular requests, things that you would like to see more examples of, or any questions about?
Can we do like a tree on something?
Sure. So like for module 2. Oh yeah, like this kind of stuff.
Either that or like module 5, the first one. Got like the basic.
Oh, like a type. Okay.
Yeah.
Oh yeah, like this one. Yeah.
Yeah.
Right. Yeah, because you could like make an official, like an actual tree code. Okay. Sure, that's a good idea. All right, I'll make up. Let's make something up. So I'm just going to say, lambda 1 dot first case. So the question is, right, how do we assign a valid type to this? And of course, this is what Haskell is doing all the time. So you could type this in and say, what's the type, and it'll make us. kind of write down a type for it, but just have it kind of be a variable that stands for some type and you don't know what that type is yet. And as you go, you might discover more things about that variable. And this is literally exactly how Haskell does this. This is kind of the way to do this. Where it says, okay, I don't know what type this is, I'll make up a variable, and then as it goes, it learns, it like fills in details. If at the end you still have some variables, then that means you can stick a for all in the front and say, well, since it's still a variable, that means it could be anything, and I didn't learn anything that said it had to be a particular thing, so I can just say that works for all types. Right? So, you know what, let's come back, let's do a much simpler one to start. How about that? Just to, like, something that we all kind of know what the type is going to be, and then just see how we would work it out, and then we'll do the, so let's say, like, lambda y dot second y. Okay. So we all know that the type is going to be something like, obviously, it's a function, it's going to be a function, so it's going to be a something arrow something, and, okay. So here's what I'm going to do. I'm going to say, all right, lambda y dot second y has to have type, well, it's a function, so it's going to have a type like alpha arrow beta, where y has type alpha, and second y has type beta, right? Make sense so far? And, well, what else do I know? What else can I look here? So this is second y. So in order to apply second to something, that thing has to be a pair, right? So y, I can even fill in, I can say alpha is equal to, you know, a pair type, you know, gamma times delta. You don't have to use Greek letters. I don't know. I like using Greek letters. Well, okay. And if y has type gamma cross delta, and then second y has type beta, what did we learn from that? No. So we know both that this is equal to delta. Right, so y is a pair where the first thing has type gamma and the second thing has type delta.
So second y is delta.
Yeah, so like second y, it says it's beta, but also we know it's going to be delta because that's the type of the second part. So actually we've now learned that beta equals delta. They have to be the same because and I don't think there's anything else we can learn. So all told, we can say the type of this is, you know, it's alpha arrow beta, but alpha is gamma cross delta, and then arrow beta, but beta is also delta, right? So like I could say this, right? And if I want, I could say like, you know, for all gamma delta, something like that. Or in Haskell, you could just write like a b to b or something like that, which makes sense. And if I wanted to maybe do this slightly more formally, right, so lambda y dot second y. And I can say, like, what type goes here? Well, I can construct a tree of a typing derivation. Right, and what rule, and maybe what I should do find this helpful, then you can do this. And if you find it, please do. Really, I guess it's just like, maybe this gives us a more formal, organized way to do the same thing we were doing above, where we were kind of just saying what we learned and trying stuff. So I look over here at the rules, right? The nice thing is, right, basically notice that for every possible thing that a term could look like, so for example, it might look like second something, or it might look like right something, or it might look like a case, or it might look like a lambda, right? For each possible thing a term could look like, there's exactly one rule. And so that's really nice because there's no guessing, right? So unlike when we were proving things just in propositional logic, there's kind of multiple rules that you could use at any given point, and you kind of have to guess or figure out what the right rule is going to be that's going to help, right? Here there's no guessing. Now with some type systems there could be some guessing you have to do. But with this type system there's no guessing at all. You just look at the term and you look at, okay, which is the rule that is about that, and then I just use that rule. So that actually makes this easier than we're doing before. So here's the lambda rule. And I guess actually notice that the way this is written, a lambda always has a type annotation on the variable, but I didn't write that here. It's kind of like, imagine it's kind of omitted, and we have to just figure out what it's supposed to be. Okay. So, well, this says, I put y colon alpha in the context. And then I have to show that second y, t, which is this t here, the body of the lambda, has some type beta, so I'll just call it beta. And this whole thing is going to have type alpha arrow beta. Okay. All right, and then what's the rule for second? Well, here's the rule for second down here. Okay, just copy the context up here, y alpha, and as long as the body, which is y, has type, now I have to be careful here, I can't just write alpha cross beta, because I'm already using alpha for something else, right? So I just have to make up a new name, right? But this beta here actually is like literally called beta. Over here, so I'll keep that. So I'll just call this. Okay. Well now, so this is the lambda rule. What rule do I have to use now? I just have a variable here, right? So I have to use the variable rule. Right, and here's where I learned something, because notice this rule says, look, if you've got a variable in the context with type alpha, then you get to show that that variable has that type. Okay. This doesn't literally look like that, right? This says if y has type alpha, then y has type gamma cross beta. So what this is telling me is that alpha and gamma cross beta actually have to be the same, right? In order for this to make sense, they have to be literally the same, which is okay, because all these variables, these like alpha, gamma, beta, right? These are just placeholders I was making up. So this could stand for anything. I don't know what it is yet, and I'm willing to learn later what it is, right? And so I've just learned something. I've learned that actually those have to be the same. So this is the bar rule, and I learned that alpha equals gamma cross beta. And so, I don't know, maybe if I want, I could like, and there's different ways to do this, right? You could just kind of keep track on the side of what you've learned about the variables, or you could literally go through and I'm going to change the color. We have to do the color palette. There's the color. I could literally go through and I've learned something about alpha, I can just go through and, replace it with gamma cross beta everywhere. Since that's kind of what it should have been in the first place. It's just I didn't kind of figure that out until I got up to the top of the thing. All right. Let's do this one. So lambda y. Context shows this thing has type, we don't know what. Well, we'll just call it. Let's stop using Greek letters. Let's use maybe I'll use capital letters. Okay, well, it's a lambda, so I have to use the lambda rule right here. So I put y in the context with type e. Then first case dot. We'll have type c. And then actually, I guess I can always go in. This is going to be arrow c. We already knew that. It's a lambda, so it's going to be a function type. Right? Okay. Now what? Now I need to use the rule for first. Right here. So that's saying, well, shows that this whole case has some product type, right? And the first of that has just like whatever the first component of that type is. So we already have C standing for the result of first of that thing. So then this type is going to be like C cross something, and I'm just going to make up a placeholder for it. So we'll call it D. Makes sense so far? Right, and like stepping back a minute, at a kind of intuitive level, if you wanted to do this more intuitively, you could just say, well, look, if I'm doing first of something, that something had better be a pair, right? So I know that case thing has to have some pair type, and then you can kind of keep reading from there, right? Or you could say, well, look, this whole thing is a lambda, so it's going to be something arrow something. Now I just have to figure out like what's the type of y, that's going to be the first thing, and then what's the type of the first case, whatever, that's going to be the second part. So let's see. Now the case rule is probably the most complicated one, right? Here it is. Definitely the most complicated one. It takes up a whole line by itself. But what's it saying, right? There's kind of a few parts to this. So what does the case mean? Right, so it really is, it's almost valid Haskell syntax. I guess the only thing that's making it not actually valid Haskell syntax is that in Haskell you have to capitalize left and right. But other than that, like it's just pattern matching on T, and then it's saying, okay, which is it? Does T look like left x1? in that case, we're going to return T1. Or if T looks like right x2, we're going to return T2. So what are these rules saying? Like, in what case does this make sense? So first of all, if you're pattern matching on T to see if it's a left or a right, then T had better have a sum type, right? Like an either A, B in Haskell. Otherwise, it doesn't make sense to pattern match on it. And then we're saying that T1 and T2 had better have the same type. Okay, and that is going to be the type of the whole thing. Because T1 and T2 are what we return, right? Depending on what T looks like, we're either going to return T1 or we're going to return T2. And so they have to have the same type, and that whatever that type is going to be the type of the whole thing, right? This is very similar to an if statement. If you say, if some condition, then A else B, A and B have to have the same type, because you're going to return one or the other, and you have to get the same type. And then what's this stuff here? Well, x1, right, when you pattern match on T, it looks like left x1. That x1, that's now a name for whatever was inside the left, and you're allowed to use that inside T1. And so when we type check T1, we have to actually add x1 into the context. Because, if we see it in T1, we have to know what type it was. And what type is it? Well, if T is an alpha plus beta, that means either it's a left that contains an alpha, so that would be the type of x1, or it's a right that contains a beta, so that's the type of x2. Does that make sense? Any questions about how that rule works? So applying it here, what do we get? We get context why we chose. Okay, so the first premise here says T has type, some type, right? And our T in this case is Y. So I need to say here Y has type. And notice here that alpha and beta up here doesn't appear on the bottom of the rule. So the bottom of the rule just says gamma. So we just need to make up two completely new names, or two completely new types. So I think I'm on like E and F or something. And we can already see here that like we're learning that beta actually has to be E plus F. So what did I write beta? Oh, my B morphed into a beta. Oh, embarrassing. Right. There we go. Okay, and then this one says, all right, Y, B, comma, X1 in this case is Z. That's what's inside the left. Right, so Z is going to have type E. That needs to show that T1, the part here, which is actually Z, that has type gamma in the rule, which is whatever the output type is, which in our case is C. And then finally, I need Y, B, Q has type F. And second Q also has type C. Okay. Here, this is the variable rule, and so we just learned that actually B equals B plus F. That's not part of the rule. I'm just kind of maybe I should write it in different colors. Okay, and here, this is the variable rule also, because we're finding the type of Z, and we have Z in the context. So here we learned that actually E equals C. Yeah. And then here, well, I have to use the second rule. And the second rule says, right, second Q has type C, then Q by itself has to be a product type. Q has type second one, right, because that's what I already have here, but I made up a new type for the first part. Okay, and this is also the, oops, also the variable rule, and we learn here that f equals g cross c. And so, filling that all in, here's what do we have? We have that that whole thing, so lambda y dot dot dot, has type b arrow c, right? But that equals what? Well, it's e plus f arrow c, but e is equal to c, so it's like e plus f arrow c, which equals c plus f arrow c. Did we put anything else? Oh, f is g cross c, so I mean c plus g cross c arrow c. Okay. So in Haskell you could write it something like, for all CG, either CG comma C arrow C. And if you type this lambda term into GHCI and you ask for the type, it'll probably tell you something like this. It'll probably use different letters than C and G, but in fact, we can try it. Type of, where did it go? Lambda y arrow first, case y of left right okay, we messed up. Yes. Close. Oh, I see where you messed up, right here. I just saw the C on the edge there, but it was actually C cross D. Okay, let's fix it. So right, because that was supposed to be the type of the whole case, which means that both of these things have to be that same type, right? This is C cross D, C cross D. Okay, so E is actually equal to C cross D, right? And then this actually should have been, I'm writing a space here. Right, this C here should have actually been C cross D. So this is actually like G cross, sorry. In case, this is now G cross C cross D. So, yeah, there's just like another cross D, so this is G cross C cross D there. And, but this is also C cross D.
Interesting to be implies on the bottom one.
Yeah, it is. So, you get it right now? So it should be something like either, yeah, so A1 here is the same as our C. So C cross D, so D is, our capital D is the same as lowercase d here, and here we have G is A2 cross C cross D, that's the same as here, C cross D. And then arrow A1, which should be C, yes, okay, so good. So hopefully that helps see how to kind of do this one. Also, you should definitely feel free to use GHCI to check, right? So, you know, if you just turn in something that just says, here's the type, and you don't explain how you got that, like, I need you to show me how you got it, but feel free to check it with GHCX. So you should know whether you're right or not, right? Or you know kind of what the right type is supposed to be, and that can help you kind of figure out how you would reason the right thing, right? Cool. What else? That took a while, but that's hopefully, that was okay. Helpful. What else? Anyone want to go over? Oh, sorry. Oh. Yep, that's.
Can we just write a function in there to come up with this?
Sure. Sure, sure. Yeah, so let's see. Um, do a few things with lists. So remember that the way we're representing things in lambda calculus is we're representing them as their own folds, right? So fold R for a list, so right, it takes two arguments. One is the thing you should return for the empty list, and one is the function that says how to combine the first element with the result of folding the rest of the list. So, for example, the list like, let's say 1, 2, 3. Well, let's write down. Let's write down some numbers real quick. Well, does it matter? No, it doesn't matter. The list like A, B, C. So I'll just do make up symbols A, B, C to represent elements of the list. Doesn't matter what they are. We would represent that as, well, a list is a fold, right? So it's going to take, you know, an F and I'm going to call them C and N for cons and nil, right? So a list takes those two things and then it returns the result of folding over the list. So it returns something like C, cons A, cons B, cons C. So a list is going to look kind of like that. So it looks, I mean, right, this looks like a list with cons and nil, except the point is like, a list kind of lets you choose what you want to use for cons and for nil, instead of having some like specific constructors that you use. Just like whatever functions you want to give, I will then use those functions for cons and nil. Okay. Well, so let me just define it. So. Right, so maybe we could write like a list length function, and it should return 3 on that one. Although we haven't defined numbers. So. Okay, fine, let's define numbers quick. So lambda s lambda z, successor, A takes a number, and then it returns don't think length is one of the ones on the homework. Well, length is supposed to take a list as input, so we'll say lambda L. And now we need to return the length of the list. The only thing we can do with a list is, I mean, it's a function, right? So we can apply it to some arguments in order to do a fold. So whatever we would do using fold R in Haskell, we can do just by like applying the list itself to some arguments. And so a good way to do these, if you haven't already finished these or are still working on these, is to try implementing them first in Haskell using only fold R. And if you can do that, then you can kind of translate it into lambda calculus by, you don't actually call fold R, you just use the list itself. So to find the length of a list in Haskell, we would say fold R. Well, the second argument would be 0, that's the length of an empty list. And the first argument would say, you know, it's a function that ignores the element and takes the length of the rest of the list as the second argument and returns 1 plus that. So I should be able to say like, oh, we haven't defined plus. Well, I guess we have successor, that's all we need, right? We don't need plus. Oh, okay, something 0. The something says lambda A, take that first element which we don't care about, and then we're going to take the length of the rest of the list, and we're going to return successor n. Alright, so if I say the length of X list, that should give me back a number, so I'm going to apply it to S and Z just so it'll fully reduce and I can see what number it is. SSSE, great. How would we do, like, let's see. I don't like append. You know, append like plus plus in Haskell, right? That takes two lists and appends them. How would I start with this? Yeah, I mean, it's going to take two lists, right? So I could say like L1, L2. And then, of course, I just have to decide how would I do append using fold R. I don't remember if we did that as an example. A cute way to do it is you fold over the first list, and you say, when I see the empty list for the first list, I'm going to replace that with the second list. And every cons in the first list, I'm just going to replace with the cons again. So it kind of builds up the same list as the first list, but for the empty list, at the end, it just replaces it with the second list, and that gives you an end. So I can do that by saying, all right, I'm going to fold the first list, meaning I'm going to apply it to some arguments. The second argument is going to be L2 itself. And the first argument says, we're going to take first thing and the rest of the list, and we're going to return cons. Well, actually, yeah. And I could also just write, instead of writing lambda A, lambda L, cons A, L, I could just say cons. Now, we haven't defined cons yet, but we can do that in a second. Just say cons. The lambda calculus evaluator doesn't care that we haven't defined cons yet. How do we do cons? Well, cons takes an element and the rest of the list, element and list, right? It's going to return a new list. And what is a list? Well, a list is a thing that takes, it's a fold, right? So it takes some cons function, or it takes a function that you want to use for cons, and it takes the result you want to use for nil. And what is it going to do now? It's going to say C on n. Well, n is well, C takes two arguments, right? It's going to be like the element that you want first and then the rest. I just said like A's, CN, right, that would just mean, that would basically just give back the list A's. But I actually want to call C again on A, all of that stuff. So remember, the goal of a list takes a C and an N, and it's going to return something like C of something, of C of something, of C of something, of C of something, of N. Right, that's the goal. And so, well, the first thing, I want to say C of A, because I'm supposed to return a list that has A as its first thing. C of A and the rest of the list. And what is the rest of the list? Well, it's whatever A's is, right? So I'm just going to fold over A's and say, hey, use C and N. So it's going to say, okay, fine, C of whatever, C of whatever. Okay. So if we now do append next list, I'll give me back a list, right? It's like in the form of a fold. If I say CN to fully apply it, well, C is a bad name because font A, B, C, A, B, C, no. And I'm fully aware that I was going to do that kind of quickly. Part of that is we're almost out of time, and part is it's all video recorded, so go back later and like pause and play me on like half speed or whatever you want. Any last thing you want to see? Oh, that's a couple minutes. All right, well, hopefully that was helpful. So no class on Wednesday. We may do something similar to this on Friday. Let me know. You can be thinking if there's things you want to see, specific examples you think would be helpful. Do that. You can just come to class with a suggestion, or you can send me an email.